using the differential form of the Reynolds transport theorem and using momentum as the entity of interest, I was able to get this equation. On the left hand side, you have density at a given location x at time t, and then I have the material derivative operator of V1, which means it is what? A1, acceleration of a particle, fluid particle, which is at location xt. That is on the left hand side. It is like what we used to have in mechanics. If I give you a particle, you write F equals ma or ma equals F, right? That kind of condition or that kind of equation we have now. Left hand side I have acceleration. Instead of mass, I have mass per unit volume. And on the right hand side, I have force per unit volume. That's what is appearing here. If you check the units of this. Forces are of two types. One is the body force, acceleration due to gravity. And then there are forces which we categorized as surface forces. Now, surface forces are expressed in terms of stress tensor, sigma. However, sigma itself doesn't appear on the right hand side. What appears are the derivatives of sigma, various components of the spatial derivatives of sigma. At which location? Again at x comma t. Okay. This is a fluid particle that is at location x at time t. Okay. And all these quantities, derivatives of sigma, etc., are all at this point. V1 that is appearing there is on at this point, and density is also at this point. The derivation started with a control volume, cuboidal control volume, but eventually the equation that we get, it becomes the equation of velocity following a fluid particle. And there is no contradiction in this. It's not that we started with a control volume, then why are we interpreting it for a fluid particle? I started with a control volume, but the algebraic form is this, and then I can interpret this operator as change following a fluid particle. So control volume was an intermediate step only before we get this equation. Now the derivation that I made so far, I showed you the steps. Actually, I didn't make even the I didn't make the full derivation, but I showed you all the key steps. The equation that I am getting eventually is equation for V1, one component or the first component of the velocity vector. Velocity is a vector, so it has two more components. I would like to derive the equations for those two components as well. I would like to have the final form. One way is to actually perform all the steps that I did for V1, and the other way is to recognize the pattern here and get equations for V2 and V3 also. Are we in a position to do that? If I want to get equation for V2, what will that be? Recognizing the pattern only. Left hand side I will have this. What should I do to this? rho G2, right? Now this was straightforward. This is not that straightforward, but I think you can still see a pattern. What should I change here? This term. Sigma 1, 2. And then नीचे कुछ भी नहीं. Okay. So this force is coming because of the surface forces that must be appearing on that small fluid element, right? But that small fluid element had 6 surfaces, cuboidal. ये contribution 2 surfaces से आ रहा है. Can you tell me which 2 surfaces must be? Expression तो लिख दिया हमने pattern recognize करके. Can we infer also that, can we try to infer which 2 surfaces are contributing to this force? No, I think I have not written it correctly. Sigma 1, 1, 2, 1, 3, 1, 1, 2. Del sigma. ठीक है. Del sigma 1, 2. ठीक है. Yeah, which 2 surfaces? कौन सा 2 surface? S1, S2, S3, S4, S5, S6. Let's go back here. यहाँ पहले देखते हैं ये contribution कहाँ से आ रहा होगा. Del sigma 1, 1, del x1, which 2 surfaces are contributing? First of all, this is force in which direction? One direction. But one direction force on that small fluid element can come from any of the 6 surfaces, right? So कौन से 2 surfaces ये contribution कर रहे हैं? S1, S2. And because of S1, S2, S1, S2 both have unit vector along E1, plus E1 or minus E1. वो E1 यहाँ है. I have to go back and see the derivation, but this much understanding we should have looking at the expression. And this derivative is also coming, this spatial derivative is coming because S1 and S2 are displaced from Q. What was Q? The centroid of the fluid element or the control volume. S1 and S2 you get by displacing yourself in E1 or plus E1 or minus E1 direction, right? So that's why you get these two, this one here. So in this and this will always be the same. That's what is happening here. This is coming, this is the force in one direction that is coming because of the contributions from S3 and S4, which had unit vectors along plus minus E2. This is coming, this is the one contribution, one force coming from 2 surfaces, S5 and S6, which had unit normal in plus minus E3 direction. All right. Now let's come to this part, this expression. So this is force in 2 direction that I know from here. And that is making sense because I am talking about V2. Now I am asking this question, from which surface? S1 and S2, because ये दोनों 1, 1 है, right? So contributions from S1 and S2. Then the second term will be sigma 2, 2 del x2, and the third will be del sigma 3, 2 del x3. This will come from S5 and S6, and this will come from S3 and S4. If you have any questions, please ask. If not, then let's also write dv3 dt. Rho g3, again straightforward. आगे क्या लिखना है? Del sigma 1, 3 del x1 del sigma 2 3 del x2 del sigma 3 3 del x3. Again, my favorite questions, I will ask, this represents a force in which direction? Contribution from which surfaces? I will give you a figure. वही वाला figure S1 S2. Okay. Please have that kind of clarity. So in this way, I get all the three equations for V1, V2, and V3. This slide shows the summary of the work that we have done so far in deriving various equations. The first equation was of density using which law? Reynolds transport theorem तो हो ही रहा है, सब में use हो रहा है. But then based on entity we use a different law, right? For reason 2. Conservation law of conservation of mass gave us this equation. Okay. Also called the continuity equation. And then I have shown you how to derive the three equations for V1, V2, V3. Now what I have written here has two small minor differences compared to what I have there. First thing is I have taken density there, the density is appearing, see where the density is appearing. I divide everything by density. Then what happens? This left hand side becomes free of density. This term becomes free of density. Now here, this is the other minor difference. V1 is same as G1. V2 is same as G2. V3 same as G3. It's a set of notes that I prepared earlier. Later I made it G1, G2, G3, but today I'm using my previous set of notes, but they are same. Okay, so that I had rho times G2, rho times G1, rho times G3, so that cancels out. You are left only with G1, G2, G3 appearing as B1, B2, B3, and then this term, the stress terms get 1 by rho there. You can always do that. Density is not 0. If density becomes 0, a continuum assumption itself will break down. We do not deal with such issues. Okay, we will call this V1 equation, we will call this V2 equation, and we will call this V3 equation for quick reference. In some texts, you will see the use of a different phrase to describe these equations. The first equation, the V1 equation that we have, they would call it as, I think in my book also I call it sometimes transport equation of V1. And similarly, transport equation of V2, and so on. You may recall that the first equation, I was once giving many names to that, and one of the names was, of course, continuity was one of the names. Other name was transport equation for density. Okay. So the point is, I mean, the way we name, we start calling any equation as transport equation in fluid mechanics. If you get an equation which on the left hand side has this form, if you write any equation, if you get any equation in this form, you call this as the transport equation of psi. Psi is any tensor. Basically material derivative. Left hand side में जब material derivative आ जाएगा, we call it transport equation. Now on right hand side, you will have very different things. Look at the transport equation of density, what is there on the right hand side. Very different from what you have on the right hand side of transport equation of V1. So right hand side could be many things. And then we also refer to these terms as processes. First process in the transport equation. Second process in the transport equation of this. You can call it like that. Generally, this grouping on the right hand side is done based on some physics, some common physics. For example, if I go to this equation and if I want to identify different processes, one way is that you call this as the first process, this you call as the second process, third process, and fourth process. Four processes you can say there are four processes, but generally, if I have to refer these terms using the term process, I would group the terms based on some common physics. I will call this as one process because this is based on body forces. These are all surface forces. So typically I would group all of them together and I would call that as second process. And the second process has the physical basis that these are the forces that are arising because of surface forces. Okay. So there is no unique way. I mean, this is sort of it depends on who is writing the book or who is talking about these things. But yes, general thing is that physics-based categorization is typically done. All right. Again, I am writing that all the quantities that are appearing in these four equations, keep in mind they are at location x, comma t. Okay. We have obtained so far four equations, four scalar equations, four scalar PDEs we have obtained. Recall what we wanted to do. We wanted to get equations for V1, V2, V3, density, temperature, and pressure. So these are still remaining. We need to get equations for them also. That's what we will do next. But besides these variables, there is also a problem that we have created for ourselves. We wanted to get equations for V1, V2, V3, and that we got, but we have created a new variable, new tensor variable, जिसमें 9 scalar components. All right. So we will have to also address that question. What exactly sigma depends on? We will do that in the coming days. Okay. One more thing before I start deriving equations for temperature. Lot of writing, lot of space this is taking. You can think of conveying the same information using index notation. For example, this equation, which is right now having 1, 2, 3, 4, 5, 6, 7 terms, I can write in a more compact manner like this. I hope you would agree with this, following the rules of index notation. Does it look correct? यहाँ एक summation है, 3 term यहाँ compact हो गया, another 3 terms compacted here. Now keep in mind that when I'm writing an equation like this, k is a dummy index here also, k is a dummy index here also. Once upon a time we set a rule for ourselves that किसी भी term में कोई भी index 2 बार से ज्यादा नहीं होनी चाहिए. Am I violating that rule in any way? किसी भी term में, in any term which you are writing using Einstein's summation rule, an index cannot be repeated more than 2 times. Am I violating that when I use k here and k here? Not violating that. Because एक summation में k 2 बार से ज्यादा नहीं होना चाहिए. ये summation में k 2 बार से ज्यादा नहीं. The scope of k, or whatever a repeated index means, the scope of that meaning is restricted to this. Once you go to another term, that k has no role to play. इस k का स्कोप सिर्फ यहां तक है और इस k का यहां तक है. I am not violating any rules. For that matter, you could have chosen any other index like del vi del xi. We choose कर सकते थे. Would have also been fine. But using k here, given the fact you have used k here, is also fine. Not violating any rule. Okay. Fine. Now let's have a look at these three equations. And I am trying to write now one single equation which will act as proxy, representative of all three equations. Instead of writing all these three equations separately, I am going to write using index notation just one single equation with which anybody, if I write, you should be able to generate these equations, three equations from that single equation. Look at that. This is that single equation. Where what is appearing now is a different kind of index, not a repeated index bhi hai, but there is another type of index that is appearing, which I told you about earlier. When an index appears in a term only once, that possibility is also there. What did I call that? Free index. I am using the idea of free index. Free index is not repeated, appears once, and it tells the user, the reader, that you can choose that index to be one at a time from the range 1 to 3. एक बार करके 1 2 3 में से किसी को भी चुना जा सकता है. ठीक है. So del vi dt मैंने लिखा, free index है. You choose I1, you will be talking about this equation. You choose I2, this equation. You choose I3, this equation. But one at a time. सब एक साथ नहीं होगा. But वो one at a time का जो 3 set बनेगा, that is all represented by this. Okay, let's move to the next second term. My claim is that this is representing this group or this group or this group depending on the value of I you choose. I को 1 चुनोगे तो ये sum दिखाएगा. Is it showing that? Everybody sees that happening there? Vk del vi del xk. A repeated index for every I, every chosen I. Fine. Next term, b1, b2, b3 था, that goes as bi. Free index. Now I is a free index. It means it will appear only once in every term. But if you are talking about an equation in which an I index is free index is appearing, keep in mind that that free index should be the same in every term and on the left hand side and right hand side. One free index in each term. On LHS and RHS, that free index has to be the same. What am I trying to say? I'm trying to say when you are writing this equation in this Einstein notation, you are using free index. You chose to use free index as I here. Now, by the time you reach this term, you cannot change that free index. You cannot write bj here, arguing that j तो अभी भी एक free index है. अगर मैं bj भी लिख दूं वहां पे तो वो j तो एक ही बार appear हो रहा है. You can say it is a free index, but then your equation is not making sense. Because if you give the reader this freedom कि I 1 2 3 हो सकता है और j भी 1 2 3 हो सकता है, the reader may make the mistake that for this he chooses I1. And यहाँ पे जब आएगा तो he again has the freedom, he chooses j as 2. Will that be what you want to have? वो तो नहीं हो रहा है. यहाँ 1 है, ये भी 1 है. कहने का मतलब है once you have chosen I here, that free index has to appear wherever that particular index was appearing. जहां जहां 1 आ रहा था वहां I ही आएगा, j नहीं आ सकता. Okay? That's what is happening here. Let's go to the next second term. Second term on the right hand side and see whether what I have written here using index notation is in line with whatever it is supposed to mean or not. You check, you yourself check. Does it look okay? Del sigma ki del xk. Will it be the same if I write del sigma ik del xk? Same चीज होगी? No, it will not be. अभी तक तो नहीं है. अभी तक मैंने कुछ भी नहीं कहा है टेंसर के बारे में. I mean, it is a second order tensor, that's all. Del sigma ki del xk is not the same as del sigma ik del xk. Totally different thing. Yes, in future, if I tell you for some information, I give you that yes, sigma, the stress tensor, is a symmetric tensor. Then it can be forgiven. I mean, your mistake, your oversight can be forgiven. You will be all right, but not now. All right. So this is how we will represent it. The other point I think I must mention, you have the freedom to choose the identity of the free index. All right, I यहाँ पे ले लिया, J ले लिया, S ले लिया, P ले लिया. But there is one choice which is prohibited in this equation as far as the choice of the free index is concerned. In this equation, at least one choice. वो choice कौन सा है? क्या आप नहीं ले सकते हो I को यहाँ? I K. You should not. क्योंकि अगर K लोगे तो ये मीनिंगलेस हो जाएगा. K लोगे तो ये मीनिंगलेस हो जाएगा. ठीक है? अगर यहाँ K लिया था, यहाँ S ले लिया किसी ने, वो भी सही है. डेल सिग्मा S और S यहाँ है. इन दैट केस I S भी नहीं हो सकता है, कि फिर ये मीनिंगलेस हो जाएगा. All right. So now we move towards getting an equation for temperature. Temperature means temperature, the equation of temperature will emerge when I apply first law of thermodynamics to that control volume, cuboidal control volume. Yeah, so this derivation, some of the steps I'm going to show you. I'm going to derive nothing on board because it takes too much time. But some of the steps, like before, I'll show here. And some of the steps I am going to leave for the next PS. Okay, this is how this will be. You will be learning about this equation. So we start with the general equation of the form, general RTT equation of the form this. This is the differential form of RTT, right? Differential form of RTT with phi as the general entity, entity per unit volume, referring to that small cuboidal control volume. Now I'm going to make a choice about that entity. The entity is going to be total energy. Total energy means kinetic energy plus internal energy. The entity is the total energy joules residing inside that control volume at this given time. So kinetic energy, total kinetic energy plus the internal energy that is residing inside that control volume. Now, if you choose the entity to be total energy, phi is going to become, in general, it is a tensor, but now it is going to become a scalar, and that scalar will be total energy per unit volume. Earlier, we have written an expression for that, total energy per unit volume, that is going to be this, what I have. Rho times CVT plus rho times V dot V by 2. This part is the internal energy per unit volume, and this is the kinetic energy per unit volume. T is temperature, and CV is, what is CV? Specific heat at constant volume. The frame in context is ground frame, inertial frame, and our working coordinate system is going to be a Cartesian coordinate system, which is frame embedded, which I'm showing here. Q again has these coordinates x1, x2, x3, which is the centroid of the control volume. Now, the differential form of RTT has two reasons, reason 1, reason 2. Reason 1, and let's recall what reason 1 was: rate at which total energy is being poured or being transported into the control volume due to the advective flux caused by the Eulerian background velocity field, okay, through the 6 surfaces of the control volume. Reason 1 तो हमेशा ही वो रहता है, advective flux of that entity through the control surface. Reason 2 in general is other reasons because of which the rate of total the total energy will increase. For reason 1, we have derived the mathematical expression for once and for all, and that expression is of this form, where phi is the entity per unit volume. We made this derivation long time, 3 classes ago. So reason, to get the mathematical form of reason 1, all you have to do is to replace phi in this expression, and we are done. We will let it appear in the equation and then we will simplify it later. But right now, nothing new needs to be done for that. We keep it in reserve. We keep it on standby. Let's focus on reason 2. I have said this before also. Answer for reason 2, or the understanding what reason 2 is, comes from the first law of thermodynamics. Reason 2 is W dot plus Q dot, where W dot is the rate at which all external forces do work on the fluid element or the chunk of mass that is currently residing, occupying that control volume. And Q dot is the rate at which heat is being added to what? To the mass that is currently residing in that control volume or the fluid element. Right now there is a fluid element there. Okay. Now W dot, to get the expressions of W dot, we will again remind ourselves that forces themselves are of 2 different types, body forces and surface forces, and thus the work done by the forces can also be categorized as the work done or the rate of work being done by body forces and rate at which surface forces do work. We will get expressions in 2 steps here. Q dot can be due to the conduction through 6 surfaces. And there could also be some non-conduction reasons of heat addition. You understand conduction, right? It's easiest to visualize this in context of a solid. If I take this rod, heat it on this side, after some time you will feel that you will see the temperature on this side is rising, right? Despite the fact that no continuum material has been transferred. Yes, stationary here, but still you feel the heat here. Okay, energy is being transferred. Who is responsible for this kind of transfer or rise in temperature? What is the mechanism of by which it is happening? Conduction of heat. But I mean, थोड़ा सा और डीप जाए तो who is making it possible? मतलब मेरा आर्ग्यूमेंट है कि मास जो कंटिन्यूम लेवल पे है वो तो मूव नहीं कर रहा है, तो आखिर इस पॉइंट को कैसे हाउ डज दिस पॉइंट गेट अ हायर टेम्परेचर? वाइब्रेशन ऑफ मॉलिक्यूल्स, राइट? मॉलिक्यूल्स सॉलिड के वाइब्रेट होते हैं, यहाँ पे वाइब्रेट ज्यादा होते हैं तो उसके साथ वाले भी ज्यादा वाइब्रेट होने लगते हैं, फिर उसके साथ वाले, तो इस तरह से you get higher temperature here. But in metals, there is another mechanism by which this conduction happens, and that is why metals are more conductive. I'm talking about heat only than what we call as insulators or non-metal. एक और mechanism है, एक तो अपने vibration का, metals में एक और तरीका है. You know this, you have learnt it. बिल्कुल फ्री इलेक्ट्रॉन्स, फ्री इलेक्ट्रॉन्स, फ्री इलेक्ट्रॉन्स यहाँ जो है फ्री इलेक्ट्रॉन्स उनकी काइनेटिक एनर्जी बढ़ जाती है, वो आगे जाते हैं और इधर भी काइनेटिक एनर्जी बढ़ जाती है. तो दिस इज अबाउट सॉलिड. फ्लूइड्स में भी ऐसा होता है. फ्लूइड्स में molecules as such are not vibrating. Molecules actually have some freedom to move. Nonetheless, they do move, right? तो जब वो यहाँ पे जब हमने टेम्परेचर लगाया, हाई टेम्परेचर किया, तो काइनेटिक एनर्जी ऑफ मॉलिक्यूल्स इंक्रीज हियर. Even though the bulk of the fluid is not moving, the molecules still keep moving, right? Colliding with each other. So in that way, molecular kinetic energy increases, and that's why conduction will happen in fluids also. That is what I am referring to here. Okay. Non-conduction region. An example of a non-conduction region, how heat can be transferred. Radiation, right? Electromagnetic waves से होता है वो. इसके लिए कोई molecules की भी जरूरत नहीं है, right? So these two could be the reason. You can have a fluid which is so high, which is having so high temperature that it may radiate out heat. Yeah, that's what happens when a re-entry vehicle like space shuttle वगैरह जब वापस आते हैं अर्थ में. I was talking about this earlier also. The gas, air molecule, the air medium around the space shuttle, when it is re-entering, it is at such a high temperature that radiation becomes important. मतलब दूर लोअर टेम्परेचर है, एयरक्राफ्ट के स्पेसक्राफ्ट के आसपास बहुत हाई टेम्परेचर है, तो रेडिएशन इज आल्सो इंपॉर्टेंट. सिग्निफिकेंट अमाउंट ऑफ हीट ट्रांसफर विल हैपन रेडिएशन. But for this class, let us assume that the non-conduction regions are zero. Again, for civil engineering problems, I can't think of a case in which there is radiation is important, because radiation के लिए, as you know, the temperature has to be very, very high. तभी radiation significant होता है. Okay. So we will focus only on conduction. Q due to conduction through six surfaces. That's what we will try to bring in. That's the physics we will try to bring in. So this general physical expectation has to be converted to mathematical form. So I'm talking now about W dot. If we have a force F acting on a particle which is moving with velocity v, then rate at which the force is doing work on that particle is F dot v. We know this from APL 100. Even before that, ancient times से मालूम है आपको, rate at which work is being done is this much. उसी वर्क की बात हो रही है. W dot वही है, F dot v. But now talking about this chunk of mass that is residing inside the control volume, and if I want to get expression for W dot body force, my proposal is that this is the expression. ये V तो यहाँ आ गया. V कौन सा V है? V is at the centroid of the control volume. क्यों? क्योंकि body force, even though body force is being applied on every fluid particle, it is a volume distributed force. जैसे gravitational force है, वो body distributed force है. But then in APL 100 you have studied that if there is a body distributed force which is also a parallel force system, you can replace that distributed force by one single force acting where? जिसको center of mass भी कहते हैं. That's what I am doing. So B जो act कर रहा है वो यहीं इसी point पे act कर रहा है, and that is why to get this work done, I need to dot that force which is acting here at the centroid with the velocity of the center of mass or the centroid of the control volume. That's what I'm doing here. यहाँ B क्या है? B is, what should be V? B, what should be B? G vector ही है. That's all. Body force per unit mass vector. I should write it somewhere. That's how I use the index B actually. This I'm used to keep it even more general, not necessarily gravity, but any body force. B is body force per unit mass vector. And if it is gravitational force, then it will simply become G. Am I right? Per unit mass है या per unit volume है ये वाला? Mass होगा? ठीक है. So B dot V हो रहा है. So I'm now using the index notation. Since I'm using Cartesian coordinate system, I am going to write it as VI. V dot V will become VI. And then rho times delta x1, delta x2, delta x3. Unit is joule per second. You can check that. It has to be. Will turn out to be joule per second. VI is sum of 3 terms. Done. Body force हमेशा ही straightforward होता है क्योंकि the body force per unit mass vector itself that we come across is a very straightforward, has a straightforward expression. Done. Now again the challenge would come getting W dot surface forces. Let's work on that. So W dot surface forces, I am first writing that expecting it to be have 6 different types of contribution, and those 6 types of contribution or 6 contributions are coming from the 6 or those 6 surfaces or control surfaces that enclose this cuboidal control volume. W dot S1, W dot S2 all the way to W dot S6. वो S1, S2 मैंने यहाँ बनाया नहीं है, but वही है. S1 will be the surface which has outward normal in plus E1, S2 will be the surface which has outward normal in minus E1, and so on and so forth. Okay. Now here I want to make it clear that I am writing it like W dot S3, but these are not those indices. Einstein summation वाली चीजें नहीं है. These are just like alphanumeric identifiers of the surfaces. So don't get confused with the index notation. There is no index notation in that way. Okay. So I am going to again follow the same strategy. I will put a lot of effort, full effort for a pair of surfaces. And once I have the final expression from those 2 pair of surfaces, I will try to recognize a pattern, and I should be able to write contributions from this pair and then this pair, right? So S1 and S2. First, I am trying to find the velocity vector at A. What is A? I've not written here, but I have talked about such a thing earlier also. That's why I feel like asking you, what should be A? A क्या लग रहा है देखने से? A एक point है. कौन सा point है? Centroid of S1. क्यों मैं सेंट्रॉइड के पीछे पड़ा हूं या सेंट्रॉइड के को ही क्यों यूज कर रहा हूं? ये मैंने एक्सप्लेन किया था लास्ट टाइम जब मैं मोमेंटम इक्वेशन की बात कर रहा था. In reality, all surface forces are distributed forces. All right. But जो मैं surfaces ले रहा हूं that are very small, I can make them as small as possible. So I say that the surfaces are so small that the distributed force on that surface, I am approximating that distribution to be uniform. And once you have a uniform distribution, uniformly distributed forces on a surface, you can remove the distributed force system and put a single force vector acting where? At the centroid. That's why centroid is important. So work done में भी मैं वही चीज करूंगा क्योंकि that is a absolutely exact replacement. Equivalent force system, as the name suggests, वो equivalent ही है, same ही effect आएगा. So I am going to focus on A. That's why since I'm going to focus on A and I'm going to put the forces, surface forces, all surface forces acting at A itself, I need to find the velocity of it because eventually मैं F dot V करूंगा. Force dotted with the local velocity vector. So first let me get the expression for V. My claim is this is the V expression at A. I am using truncated Taylor series up to first order with the base location as Q, centroid of the control volume as usual. And then I am writing the full velocity vector at A in this manner. Please check this if this is right. Does it look right? सारे derivatives with respect to x1 है. क्यों है? You were asking the question class के पहले. क्योंकि a जो है because a is displaced from my base location only in even direction, and that's why all derivatives with respect to x1, but derivatives of what, depending on the quantity I am chasing. यहाँ E1 है तो V1 चेज कर रहा हूँ, यहाँ E2 है तो V2 चेज कर रहा हूँ, यहाँ E3 है तो V3 चेज कर रहा हूँ। और फिर ये डेल्टा x1/2 क्यों आ रहा है? क्योंकि B displaced है A से डेल्टा x1/2 in even direction, so that displacement is appearing to be the same in all the three components of velocity. ठीक है, V आ गया. Now let me find F at A. F at A, my claim is that it is this expression, यहां से लेकर यहां तक. इसमें क्या है? पहला ए वन कंपोनेंट की बात कर रहा हूं. ऑन सरफेस S1, force, surface force in one direction, surface force in two direction, and surface force in three direction. Force is a vector, so E1, E2, E3 है. Now E1 के along I will use stress tensor or the relevant components of the stress tensor to get that force component F1. So since I'm going to use the stress component, that has to be multiplied by an area. Which area? Area of face S1, that is delta x2 delta x3. और जब मैं टू फोर्स पे जाऊंगा, अगेन देयर विल बी सम स्ट्रेस रेलेवेंट स्ट्रेस कंपोनेंट, बट अगेन एरिया आएगा. एरिया कौन सा? वो S1 वाला एरिया ही आएगा, तो वो एरिया वही होगा. 2 में और 3 में भी वही एरिया है, तो एरिया इज कॉमन डेल्टा x2 डेल्टा x3. that much is clear. Now the more challenging or a little less straightforward thing is to get the right expression for sigma. My claim is that in one direction on S1, in one direction जो फोर्स आएगा उसके लिए सिग्मा 1 की जरूरत है. सिग्मा 1 सिग्मा का पहला इंडेक्स 1 क्योंकि S1 की बात हो रही है, और फिर 1 दोबारा क्योंकि ये वन कंपोनेंट की बात हो रही है. बट उसी सरफेस पे टू कंपोनेंट भी है, तो तब क्या बात होगी? सिग्मा 1 2. और फिर उसी पे सरफेस पे 3 कंपोनेंट फोर्स भी है, तो सिग्मा 1 3 की भी बात होनी चाहिए. दैट इज द थर्ड टर्म. ऑलराइट, सेम थिंग लाइक प्रीवियस, जहां ट्रंकेटेड टेलर सीरीज भी यूज करना पड़ेगा, क्योंकि ये सिग्मा 1 और ये सिग्मा 1 2 और ये सिग्मा 1 3 कहां पे है? sigma 1 sigma 1 1 1 2 and 1 3 are stress components at which point? Centroid of volume. वो मेरा बेस लोकेशन है और मुझे अभी चाहिए एट ए, तो ठीक है, टेलर सीरीज से, ये ट्रंकेटेड टेलर सीरीज से ले आए जैसा कि वेलोसिटी में किया था. ठीक है, तो आई हैव द एक्सप्रेशन फॉर v वेक्टर, आई हैव द एक्सप्रेशन फॉर f वेक्टर. अब f डॉट v करते हैं. देयर आर लॉट ऑफ टर्म्स, बट व्हाटएवर इट इज वी विल हैव टू हैंडल. तो 3 टर्म्स इधर से, 3 टर्म्स इधर से आ रहे हैं, 9 टर्म्स होंगे. व्हाट आई हैव रिटन हियर, नहीं 9 टर्म्स नहीं, डॉट है ना, तो 3 ही टर्म्स रहेंगे. सॉरी, इट्स अ डॉट प्रोडक्ट. सो दैट्स व्हाट इट इज. डॉट हो गया सीधे सिग्मा वाला कंपोनेंट और v1 सिग्मा 2 सिग्मा 3. derive, again reminder, unless you derive it once you will not get the familiarity and understanding, and while you derive many questions will come, and those are the opportunities to take your understanding deeper. So this is w dot s1. w dot s2 मैंने सीधे लिख दिया है based on this expression, but with some additional understanding. More or less it looks the same except for some negative signs coming. Let's look at those signs first. Why is the negative sign here? Reason, यहाँ प्लस था, ये माइनस हो गया. क्यों हो गया? क्योंकि ये, yes, S2 is, if you get to the centroid of S2, you go along minus E1 direction, delta x1/2. तो ये माइनस 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 यहाँ सब इसलिए आ रहे हैं क्योंकि सेंट्रॉइड ही उस सरफेस का माइनस E1 डायरेक्शन में. और ये माइनस क्यों आ रहा है? ये माइनस क्यों आ रहा है? अगेन जब मैं मोमेंटम इक्वेशन की बात कर रहा था तो आई ट्राई टू एक्सप्लेन इट ऑन फ्राइडे ऑनलाइन. ये माइनस क्यों आ रहा है? ये माइनस, हाँ, नो इट हैज नथिंग टू डू विद वेलोसिटी। अच्छा ठीक है, तुम दूसरे तरीके से कह रहे हो। हाँ, फोर्स और वेलोसिटी ऑपोजिट डायरेक्शन में, ठीक है, बट फोर्स उल्टे डायरेक्शन में क्यों हो गया? सो फार इट्स राइट। क्यों हम कह रहे हैं फोर्स जो सिग्मा के कारण आ रहा है, मतलब ये वाला पार्ट एक फोर्स दे रहा है, ये क्यों उल्टा हो गया कंपेयर टू यहाँ? एग्जैक्टली दैट इज द रीजन। ये हमारा साइन कन्वेंशन है कि अगर फोर्स, और इफ वी क्रिएट अ फ्रेशली कट सरफेस और उसका यूनिट नॉर्मल और जो फोर्स डायरेक्शन है, ठीक है, वो दोनों अगर अलग डायरेक्शंस में आएंगे तो नेगेटिव होगा। मुझे फोर्सेस सभी चाहिए प्लस E1 प्लस E2 प्लस E3 डायरेक्शन में। प्लस E1 के लिए जो फोर्स लाना है, फॉर दैट इफ आई गो टू S1 आई गेट फ्रॉम दिस, यहां से लेके यहां तक में मिल जाता है। To get the force in one direction on S2 face using the same strategy of using sigma components and area, if you go only with this much, you are getting a force in minus E1 direction. All right, and that is why this negative sign is there, which in other words is the same as what you are saying कि वो negative side में force V के उल्टे दिशा में था, that's why minus is coming. Fine. So you get these expressions and then you do the algebra, many things will cancel out, like it happened for momentum equation. And then when the dust settles down, you get a very nice compact expression for this pair. Look at this. केवल 3 terms हैं. Of course, ये partial derivative, if you apply product rule of differentiation, you will get more terms, but I would like to keep it like this, very compact form.